Hi, I'm Matt Ingenthron, a Senior Director in Engineering at Couchbase, where I have a couple different teams that work on things like SDKs and connectors, what we call cloud native engineering, which includes integration with Kubernetes and Prometheus and a number of other things there, and relevant to today, distributed transactions. So I'm going to talk with you a little bit about what we've done recently with distributed transactions. So let's get started. So I think it's about 5 or 6 months ago, we introduced distributed ACID transactions in Couchbase, which is different for a distributed document database. And so I'm going to give you a sense of what our motivation was for that, how it applies to a fictitious but realistic from a data model perspective kind of application. I'll give a demonstration of that application, or really a workload generator that simulates it. Then we'll talk a little bit about what's next in the future. So first, a couple words about our motivation. Now, it turns out if you're talking about document databases, the document is sort of the natural state for a given application. In all databases, the data is really driven by the app or its users, but it goes a little further in a document database. You typically have a high-level language object model, and you can very easily decompose that to simple JSON documents or a set of JSON documents without a big impedance mismatch between the two. You don't necessarily need an ORM as an example, or some kind of mapper between the two. And that actually makes it a lot easier for application developers to do their development in the first place. You don't need to necessarily go through database migrations every time you change the schema. That sometimes in some environments might even imply downtime. So what you're seeing over here on the right is just a really basic user profile. This user has a name, they have a number of coins, a number of hit points, they have a couple of items, and then they have a friend. So there's a reference to a friend in case we needed to go retrieve that user's friends. You'll also notice that if I had this in a state where I was referring to a couple of other things, it can give us some performance and reliability advantages. If all I need is this document and another node within the cluster has failed for a period of time, Couchbase's auto failover will automatically take care of getting that node back online. But if another node has failed, I don't need to have a reference to other documents within the system to be able to service that request. I can just get it very quickly. Denormalization, which we don't really have here, but we will in a moment, also gives us performance advantages because we don't have to stitch together multiple records to be able to service that request. So it gives us performance and reliability advantages, and it really matches a lot of what's happening at the applicational high level. Now, in a document database, within the document itself, we have some of the properties of ACID, which I'll define and talk a little bit more about in a bit, including atomicity, meaning that if I want to modify multiple attributes of that document, I either modify both of them or all of them or none of them at the same time. So, we can also extend that document as needed to meet what the application needs. So in this case, on the right-hand side, the document's gotten a little bigger. Imagine that I've introduced team play within my data model. So I'm allowing multiple players to be on the same team. Maybe they're sharing items. And I want to make sure that the multiple players can't grab the same item at the same time. And we don't have to deal with a lot of the issues between those. You could implement that by just having the document represent the team instead of representing an individual player. And so Couchbase has a bunch of these supporting features already in document databases in Couchbase, as an example. Document updates are always atomic. We also have some supporting features in terms of accessing data. So we have sub-document operations. Maybe you don't want to retrieve the whole document. You just want to retrieve a particular member from the team. So you can tell Couchbase, I would like to get a particular attribute out of the document. And it can do that in a very quick way. Maybe you just want to modify a particular attribute out of the document. We also have a couple of concurrency controls. One's an optimistic concurrency control, which is really kind of about dealing with a race with multiple users trying to modify a document. So there's a fairly simple way of detecting that condition and then remediating that kind of scenario, which I'll talk a little bit more about in a bit. And then we also have pessimistic concurrency with locks. So you can acquire a lock for a document and know that nobody else is going to modify it. Those locks need to be used a little carefully because there are timeout values and so forth to protect against locks being held forever in a crash sort of situation. But it's useful if you have, say, an object model where you have objects, documents referencing each other, and you want to traverse and acquire and then update as you move back out, and works very well from a concurrency perspective for those kinds of situations. Now, one of the things that sometimes happens is people are transitioning from relational databases to Couchbase. And denormalization often works. You can often take what was represented as multiple tables in a traditional relational database and then just turn that into a document within Couchbase. And then you get, or keep, I should say, the majority of the properties that you had from ACID in that relational database still against the document itself. So this way you can have either normalized or denormalized data within Couchbase as you make that migration. Your choice depends on when you need atomicity, when you need the performance advantage, or when your object model or your document model underneath really just needs to be represented differently. And then we have the ability to give you strong consistency across those multiple documents and even extensive join support with nickel. So Couchbase works very well for these cases. Sometimes people will start using Couchbase initially as a cache in front of the relational database, and then they may actually, and we've seen this multiple times, disconnect that relational database from the background in the future. There have been situations in the past where people needed to have a relational database to carry out some of the ACID types of things and then just represent a subset of the data in Couchbase, but that's no longer the case now that we have distributed ACID transactions in Couchbase. So with distributed transactions in Couchbase, now app developers can simplify their application logic by getting all or nothing semantics from Couchbase for durably modifying multiple documents on multiple nodes. So it doesn't change any of the distributed properties of Couchbase. You get atomicity, and you can modify in the context of a transaction multiple documents. No rules about which documents you're not allowed to modify. So let's talk a little bit about ACID. ACID looms large over this term transactions in the first place. It turns out ACID is about a 30-year-old term, and when it was defined, there really is, it was defined without the idea of a distributed database. It was really kind of defined for single systems. So in ACID, there really isn't a formal definition here for modern distributed databases. And part of this is we've seen over the course of time a couple of different disciplines in computer science kind of coming together. Distributed systems are very common these days, the reality of the way we build a lot of systems in the future, but databases still exist, and a lot of the concepts from databases need to apply to these distributed systems. So those two disciplines of database development and distributed systems are kind of coming together here at once. And so terms like ACID that lived in one world now need to kind of be reconciled to work with the other, with the reality of distributed systems. So A and D in ACID are binary. You either have them or you don't, right? You're either guaranteeing the update of multiple documents at the same time on when you're carrying out the transaction. And in the case of Couchbase, that means on different nodes. And durability, you either are storing that data in a reliable way or you're not storing it in a reliable way. But that gets kind of interesting because even with durability, is stored on disk actually considered durable? Well, in a distributed system, if a particular node fails, we actually don't care about it anymore. Well, we might actually just get another node. So we might need to have different levels of durability. Maybe I'll actually consider it durable if it's in memory in 2 locations, and that's sufficient from my paranoia perspective for durability. So Couchbase actually has 3 different levels. You can either replicate to the majority of nodes, replicate and persist to disk on primary, or persist to disk on all of them, sort of max paranoia. Then we have consistency, and that implies that the integrity of all artifacts related to that transaction are maintained. So in Couchbase, consistency is automatically ensured when a transaction is performed. Some things like replica copies are immediately consistent with respect to the transaction. So obviously that's part of how we get to durability, but some other things like indexes and cross data center replication are eventually consistent with respect to the transaction commit. And we have actually always had a way with queries that are built on top of indexes to be able to enforce strong consistency upon read with request plus. So that means that when that's a parameter to a query. So when you make that query, you can say, I want that query to be with respect to all of the changes I've made. Finally, we have isolation. Isolation is really kind of a question about concurrency. If I have multiple people trying to modify records at the same time, what kind of guarantees do I have with respect to how I read the data from multiple changes at the same time? And Couchbase implements read committed isolation for concurrent transactions. So that is, we believe, and our research indicates that's the most common isolation level people are using in their relational databases. And since the term ACID has been introduced, there have been varying different levels of isolation introduced on top of that. So that's just a brief overview of how we see ACID. And I'd be happy to get into discussion on this any further. So let's talk about how this is applied to a fictitious, but maybe kind of realistic example of a document model for a Couchbase system. So we've raised some money and we're going to build a massively multiplayer online role-playing game, an MMORPG with players and monsters. So we need a data model. We are going to have players who fight monsters. And then based on that fight, win or lose, they're going to, if they win, they're going to get a weapon. If they lose, they lose some hit points. So nobody can die. You always can come back to life. You can always fight another day, but your players fight monsters. And we get our version 1.0 built. Great. Okay. Got our funding, got our 1.0 built. Problem is, we forgot to do the massively multiplayer part. There's no collaborative play. I can't have multiple players fight the same monster. So I need to fix that, right? So let's roll out a new version. So players are going to continue to fight monsters and win weapons. So we roll out our version 2.0. And in version 2.0, players can fight monsters together. So I can coordinate with my friends. We can go find a monster. We can kill that monster. But we left a bug in there. It's possible for multiple players to deliver the death blow. And the reason that's a problem is then the players of the game figure it out. And so instead of battling a monster together to death, what they do is in this massively multiplayer world, they'll battle it to close to death. And then a bunch of players will gather up together and they'll all deliver the death blow, or many will deliver the death blow at the same time. And the problem is they win items, they win multiple items. And because items have rarity, and if you don't have a certain amount of rareness for an item, the gameplay is not very interesting. This bug has allowed too many items to exist in the world, and the players are just spending time hacking the game, and then they get bored and they leave. We need to keep the gameplay interesting. So let's think about this. How can we fix this? I think what we'll need to do is probably introduce a fix. We'll still allow players and monsters, multiple players, to fight a monster. But what we're going to do is take one of those tricks that we have. We're going to take Couchbase CAS operations. And with the CAS operation, what happens is now multiple players are fighting that monster, lowering its hit points until it gets down to 0. But only one of those players is going to be able to deliver the death blow to that monster and win an item. So the way this works is if two players are trying to deliver that death blow, the application server that's handling the request is going to try to modify the document. It has to pick up a little piece of opaque information that we call the CAS. That's for check and set. And so that means that if that opaque does not match, then the document's already been modified. And so you need to retry that operation. So in the scenario that two actors within the system are trying to grab that document at the same time. What we want is one to succeed and one to fail, and CAS will give us that in a very efficient way. So we pull out that trick, we introduce CAS operations, the bug is fixed, gameplay is now much more interesting, and 2.1 does really well. So that's great. We now have much better revenue. We're doing great. We're with our new startup here. So now let's try version. We want to move on. We want to make things more interesting. So imagine now I introduce another feature. Players must now, players can still fight monsters together, but they have to do it outside the city. So you have to be outside the city wall where the players are. And if you go into the city, you will do trade in a bazaar. So this works really well at first, but then players figure something out. Players figure out that if there are multiple players and they go into the bazaar and they start executing a trade, say I have the logic that's depicted over here on the right, I'm executing a trade. The two users want to trade coins for an item, right? So imagine player one, I have to retrieve the document for player one, and I have to retrieve the document for player two. And then I have to move the sword from player one to player two. That's very easy to do in the application logic. And then I go to store that change back to the system with a CAS operation. And then I go to store the other change back, right? Sounds like it'll be great, except there's a bug. The bug here is that my players can start a trade and then disconnect. And then items that we might want to be rare are not going to be rare. They can be duplicated within the system. So if, for example, one player has the Sword of Awesomeness and they start this trade, and then they were to disconnect at just the right time, then you might have multiple Swords of Awesomeness, right? And so that might sound a little silly to you, but this is a real world problem. In massively multiplayer online role-playing games, it's called a dupe bug. And if you were to go to Google and search for a dupe bug, you'll find lots of scenarios. Here's one from just a couple weeks ago, where Final Fantasy Crystal Chronicles on Switch had to be patched because of a dupe bug. And then there was one just a few days before that. This is from a blog where a game blogger is showing people how to use this dupe glitch to get additional items within the game. Even Animal Crossing New Horizons, fairly recently had a dupe bug that allowed players to exploit this. So people figure this out in games, and if you have that, it can actually mess up gameplay, and it's not as interesting. So we need to fix this bug. How are we going to do that? Well, really, we can't necessarily go and stick all of the players into the same document. That's just not going to work. It's huge. We want this to be massively multiplayer. So we need a way to atomically modify multiple documents at the same time. So we're going to reach into our Couchbase bag of tricks. We're going to introduce Couchbase transactions. The gameplay is almost exactly the same. But what are we going to do with Couchbase transactions? And so this is the one slide in this presentation, although I'll use it twice, where I'm going to talk a little bit about the code. So what we've introduced in Catchbased transactions is, in your high-level language, this is an example of Java code, you will define the logic for your transaction. So this is a first-class function, a so-called lambda, and you'll define the logic for that, and then you'll pass that to transactions, and then the Couchbase transactions implementation will carry out the logic behind that lambda that you've specified. So in this case, as you can see, it's very simple. I'm just grabbing player one, grabbing player two. I'm doing it within a transactions context. I have to turn them into JSON objects. This could also be done with POJOs. And then I determine what the item is to trade from the game action. And then I grab that item out of, I have to determine the number of coins the particular player has. And there's a bunch of logic that's not included here in the slide. I, of course, need to make sure they have the right number of coins. Then there's a place here where we simulate what the price would be based on rarity. So if an item is really rare, of course, you would expect to pay more for it. And then what we do is we put in player one's object, player one's document, we put the number of coins and the items that they're trading. And then in player two, we remove it from the items, right? Very simple. And then we do a replace. Notice this is again against the transactions context. So every time I'm accessing the system, I'm going through this transactions context. So I replace player one, replace player two, and then I call commit. It's that simple. So from an application developer perspective, it's Couchbase's job to do all of the transactional logic. So I roll out this fix. My bug is now fixed. I've now saved the economy from ruin, and version 3.11 of my app is amazingly successful. So now let's get a little bit of a demonstration of that. Okay, so what I have here is a Couchbase cluster. This one's actually running in Kubernetes. What I have here really is a 3-node cluster, and as you can see, I'm doing about 1,000 ops a second. That's really just from one simulator of this game. And over here in Grafana, what I have is the transaction rate. So this is a per instance rate. So if I had more than one running, I'd see it, and this is the total rate. And down here, I have a latency heat map. So Prometheus, the statistics here are coming out of my application, and then Prometheus is recording them. Prometheus is a monitoring system that will grab stats and store them in time series. And then, as you can see in this most recent interval, the majority, the hotspot, the majority of my statistics or of my transactions are being done in somewhere between 1 and 2.5 milliseconds. Prometheus does everything on a per second basis when you're gathering histogram latencies. And so I can see the distribution of my latencies here of that. Now, what I want to do, I've kind of fake this one a little bit. There's a very small amount of data. So what I'm going to do is I'm going to scale up this deployment. First, let's just do a kubectl get deployment / txn examples. If I did that correctly. Oops, sorry, it's txn example. And as you can see, I have only one running. So now what I want to do is I'm going to turn that up to 9. The reason for the number 9 is I have 9 workload nodes running, 3 running in each of 3 different availability zones in the cloud that I'm using. So I'm going to do a kubectl scale -- replicas 9, and then I will do that for deployment / txn example. And so what that will do is it should turn my workload up by to 9 times the previous one. You can see currently we have 1 available, 1 of 9. Shortly we should have, there we go, we have 9 available. So we've been able to start 9 of these. So what I should see is in a little bit, and I know from experience it takes a little while for the Prometheus auto discover to discover those new nodes by label. So while that's happening, let's just have a look at what other information is available. Cool thing is, since this is Couchbase deployed inside Kubernetes, I can see a bunch of other information from that deployment. So I can see the CPU utilization of all these transaction example nodes from my deployment. I can see, as an example, where I can see where CPU is going for the last couple minutes. I can even down here see, since I just started up those new nodes, if I were to look into the memory usage, you can see that there was it was pretty steady. And then I started up a number of new nodes. We can actually even zoom in on this portion of it. And whoop, I think I clicked one time too many. You can zoom in on this portion of it, and we should be able to see the new nodes starting up and starting to consume memory in this deployment. That didn't do quite what I wanted it to do. Let's just go back to a 5-minute view. Last 5 minutes. Try that again. Look to the end, including the last 5 minutes. Should see just that portion of it. And sure enough, I see all these little transaction example deployments, all using a little bit of memory. So by now we probably have over in our example dashboard, we probably have the instrumentation from our deployment. If everything went well, Prometheus has auto-discovered it, and we'll see the new nodes. So sure enough, I've got a bunch of new nodes here. So you'll note that the overall transaction throughput has dropped per node. Sorry, I should say not overall, but the transaction throughput has dropped per node, but the overall transaction throughput has actually gone up a fair amount. Now you might be wondering, wait a minute, I went from 1 to 9. Why didn't that go up linearly? Well, that's because in this particular case, you'll remember I was doing about 1,000 ops a second initially, and I really only have 6,000 ops, or sorry, 5,000 players in the overall system. And because players are selected at random and they may conflict, we should see a much larger number of conflicts, right? But because I have this larger number of conflicts, and because the way I was able to describe my app logic, I actually don't have to do anything magical to manage that conflict underneath. The Catchbase implementation will automatically do that. So along with that increase in throughput, the other throughput that I would have gained is handled by coordinating the order of those transactions in the Catchbase transactions implementation. So what you're seeing is where in the past our hotspot latency-wise was somewhere between 1 and 2.5 milliseconds. Now our latency has gone up, but it's still very respectable. Right now we're in a 10 to 25 millisecond latency when we've increased by 9-fold the workload on the cluster. So pretty cool. So now I want to jump back over to the code and tell you a little bit about that, and also where we're going in the future. So a couple things to point out on the programming model. Same code I showed earlier. You'll notice that the programming model was flexible to the data without any changes. So as I went from one version of the application to another version of the application, both which were denormalized, and I'm able to use simple ops against Couchbase, and then suddenly I need transactions, I don't have to change my data model. I don't have to change the model underneath. Catchbase transactions just automatically handles that for me. So as I needed that atomicity across any two possible players in the system, I didn't have to reshard or relay out the data as I might have to, say, with a sharded traditional database or something like that. I can just execute a transaction across any two arbitrary objects in the system. By the way, that even extends to different buckets, because that allows you to do things like microservices, and it's going to work with collections in the future. You'll also notice that I'm able to express my application logic even in the situation where a document's already involved in a single transaction. So the Catchbase transactions implementation will coordinate those. So you might see a little higher latency, of course, because it's going to automatically handle that for you. But I didn't have to do anything special. The logic is exactly the same logic. The only thing I've left out of this is some of the checks on making sure a user or player has enough coins, that sort of thing. Finally, I'd point out that the entire system is fully distributed. So it doesn't matter if you're running with one node or 100 nodes. When you're running with 100 nodes, that transaction logic is going to be distributed across the system. And the minimal information necessary, or only the minimal number of nodes you would have to talk to in order to achieve the transaction, are involved in that transaction. And that's pretty cool from a perspective that if, say, one transaction was happening for Jane and John, and another transaction is happening for Beth and Adam, and they happen to be on completely different nodes in the cluster, there's no coordination, there's no contention for resources. Those transactions can proceed entirely independently of each other within the system. All of this builds on top of the new durability options that we have, including the different tolerances for durability or paranoia that you have for your data underneath. So let me give you a sense of where we are currently and what's next. All of this is, everything I've used here is shipping now. Catchbase Server 6.5 with Transactions 1.0 shipped about 5 or 6 months ago. Catchbase Server 6.6 with Java Transactions 1.1, mainly some performance enhancements, a couple of nice things with respect to indexes and when data is available in the system were changed in Java Transactions 1.1, and that's been shipping for, I think, 2 or 3 months now. In the near future, actually, maybe even today, as you're watching this presentation, we probably will have already been shipping the .NET Transactions 1.0 beta and the C++ Transactions 1.0 beta. So for Catchbase Server 6.6, those are all both compatible with Catchbase Server 6.6, which is already generally available. So we'd love to get you to download, try, and give us feedback on this new beta functionality. By the way, if you're familiar with a regular Catchbase, you might be wondering why C++ instead of C. Some of the functionality I was showing with the Lambda was a lot simpler to do that in C++ than it would have been to do in C. Coming up in the not too distant future is Couchbase Server 7.0, and in that we're going to add support for nickel transactions alongside the existing KV transactions, and that will be with Java, .NET, C++, and Golang. So the idea there is that then in that transaction context, you'll be able to have the full power of query. So even if you modify a few items with the data service directly through the KV commands, and then you do a query, your query will be consistent with respect to the updates that you made from earlier in that transaction. If you do an update statement against the query service, that will all happen atomically with everything else that you're doing in that transaction. So very, very cool. Something that we're going to be looking to ship in 7.0 in the not too distant future. So a couple resources for you down there at the bottom. Just go to catchbase.com/transactions, and that's where you'll be able to get a lot more information. Finally, I would tell you the transactions demo I showed is out on Couchbase Labs on GitHub, just Couchbase Transactions Java examples. I will include this in the chat if you're watching this live at Couchbase Connect, and I'd be happy to chat with you more about it. Thank you very much for attending the presentation, and I look forward to talking with you and seeing your feedback on the beta. Thanks.